Day 15 of 60 in our DSA in Rust challenge. And today, binary search is going to teach you more about ownership than any tutorial ever did. Here's the thing nobody tells you. You already know binary search. 3 lines in Python, you're done. But the moment you write it in Rust, the compiler stops you cold and asks a question you've never had to answer before. Do you want an index, a reference, or an own value? That question is the whole lesson. Watch this. In Python, you write arr, mid, compare, shrink the window, return the index. The interpreter never complains. Now in Rust, you try the naive version. You grab a slice, index into it, try to hand back the element you found, and you get cannot move out of index of vec. That error isn't Rust being difficult. It's Rust forcing you to decide what found it actually means. Let's answer that properly. First, slices. A Rust slice like t is a fat pointer. It's 2 words, a pointer to the data and a length. That length travels with it, which is why indexing is bounds checked and why you can split a slice cheaply without copying. When you binary search, you're not searching a vec, you're searching a window into it. Keeping that mental model, pointer plus length, is what makes the ownership decisions obvious later. Now the iterative version, returning option a size. We track low and high as usize. Loop while low high. Compute the midpoint. And here's the correctness trap. You do not write low plus high /2. On usize, that addition can overflow and panic. You write low plus high low /2. This isn't style. In Rust, it's a requirement, because usize arithmetic wraps or panics where you'd never notice in a garbage-collected language. Match on the comparison, narrow the window, return some, mid, or none. Returning the index is great for an interview, but sometimes you want the thing itself. Upgrade the signature to option T. Now you return some, slice mid. The compiler silently infers a lifetime here. It knows the returned reference can't outlive the slice you borrowed. You didn't write a single lifetime annotation, but Rust wrote the contract for you. This reference is valid exactly as long as the data behind it. That's the borrow checker doing your bookkeeping. Let's make it real. Generic binary search over t, where t, ord. Because we constrained on ord, the exact same function searches a vesi32 and a vec packet sorted by sequence number, as long as packet derives ord. No rewrite, no overloading. You write hashtag, derive, partial eq, partial ord on the struct, and the field order defines the comparison. One function, primitives and structs, 0 duplication. That's the payoff of explicit data modeling. The interview boss level, search a rotated sorted array. The array was sorted, then rotated at some pivot. You binary search, but at each step you decide which half is the sorted half, then check if the target lives in it. The Rust win here is match exhaustiveness. When you branch on whether low, mid, and high form a sorted segment, the compiler won't let you forget a case. An off by 1 or an unhandled branch becomes a compile error, not a 2 a.m. production bug. The type system is your test suite. Step back and see the pattern. Binary search in Rust forces you to separate 2 questions that GC languages let you blur. Where is it? Which is an index, a usize, a cheap copyable number. And what is it? Which is a reference into own data with a lifetime attached. Index for position and arithmetic. Reference when you actually need the value without copying. Own value when the caller must keep it after the slice is gone. 3 return types, 3 different contracts. Day 15 done. The takeaway. In Rust, binary search isn't about the loop. It's about committing to what found returns an index, a reference, or an own value before your code will even compile. Subscribe for day 16, where we tackle 2-pointer techniques and the borrow checker gets even more opinionated.